Okay. Let me send a quick email. Apologies for posting the link at the last minute, guys. I just want to send the email to make sure anybody else who might have gone to the other room knows that we're here. All right, I'll give people a couple of more minutes to see if they can find their way over.
So in the meantime, Dr. Siebert, did you get my email yesterday about your web server account?
Oh, yes, I did. Thank you. I didn't put the names together. The name sounded familiar, and I was like, oh, thank you, IT person, for creating me this account. And it didn't occur to me that, this IT person that I thought I was emailing is actually also someone in my class.
Yeah.
So, yes, thank you for creating the account. That's very helpful.
Okay. And also, are you still about with extending the deadline for that COVID quiz?
Yes. Yes. Code extension. Yeah, sorry about that. I will definitely take care of that for you.
Okay, thank you. I've been a lot more diligent checking it now. So once you extend, I'll probably get done within an hour.
Okay, fantastic. Yeah, sorry I'm a little discombobulated these first couple of weeks, guys. There's definitely a learning curve associated with doing this anyway, much less with doing it online. So I appreciate your patience. Okay, we're up to 14. That's looking pretty good. Let me try sharing screen. I will see if I remember to record the lecture this time from the beginning. All right, let's make Zoom big enough so that I can see everything. Participants in the chat is somewhere else. Okay. Okay, so maybe it's time to go ahead and get started. I figure we should discuss some old business. Thank you for reminding me about some old business that I did not take care of on my end. I will try and take care of that as quickly as possible for you and send an announcement once I've done it. The other old business that I think I want to bring up is that I'm going to experiment a little bit of maybe there's a better way of giving you guys the lectures. It was slowly dawning on me after the couple of lectures that I'm throwing a lot of information at you very, very quickly. And someone brought to my attention, for instance, that it's very hard to keep track of the lectures when you're trying to process not only what is written on the slides when I send them to you, but also the new notes that I'm writing on the slides as we go. So especially since we made it about halfway through the slides last time, I thought that perhaps I would try to do as close to a Blackboard talk today as possible. We can still sort of go through the slides as written before, but I'm going to try and write on a blank piece of paper as if it was the blackboard to force me to slow down and give you only one stream of information to process at a time. So I will experiment with whatever is the most effective way. Please give me feedback on what works and what doesn't work, and we'll converge in this process together. Okay, any other old business for me, things that I have forgotten, been too busy with meetings to keep up with? Okay, so if not, all right, in PowerPoint. So let's recap where we were last time. And let me get this in a place that I can write on it. Okay. So last time we were talking about using abstract algebra to go beyond the group theory or the algebra of one operation and consider fields and vector spaces where you have two. So we had talked about a couple of different examples. We talked about the differences in going from 1 to 2 binary operations. And in specific, you have to include new information about distributivity, about how addition and multiplication relate to each other. That is enough to give you a field. A field is a more powerful algebra that you can solve all kinds of equations in. The usual real and complex numbers are all fields. Also things that are weirder, the rational numbers themselves we saw are fields. There are lots of other fields that don't look like the real or complex numbers directly. As long as they satisfy these algebras, they are fields and you can solve equations with them just like they were real numbers. So we worked out some exercises. This property that a field cannot contain divisors of 0 is a very important one. So we said this is true for proper fields like the real and the complex numbers. It's also true just 1/2 a step below the algebra of fields. We haven't talked about this in class, but it's called a ring. And matrices, for instance, don't satisfy the commutativity requirements to be a proper field. But aside from that, they do have everything else, including this fact that you can't have divided of 0. Actually, let's scratch that. That is not a true statement when I think about it more carefully. The statement that matrices cannot have divisors of 0 is not correct. And there's an example. Pull it up from Schumper. So it is possible to have matrices that are non-zero that square to be 0. So just to correct my own misstatements. It is entirely possible to have, let me say, a matrix A like, what, 0, 1, 0, 0, that might do it, such that A squared is 0, 1, 0, 0, 0, 1, 0, 0, multiply it all out, and I should get 0, 0, 0, 0. So A squared is the 0 matrix. If we were being more careful in our notation, we might call that the ket 0, even though A itself is not the 0 matrix. So I should have thought more carefully before I let those words come out of my mouth. Matrices do not possess this property. Matrices can have divisors of 0. This specific example where you have one matrix and its square is 0.
Dr. Siebert, you aren't recording.
I did it again. Sorry. Recording.
This meeting is being recorded.
Okay, once more. Okay, again, apologies for the recording. You guys are getting faster and faster at this, but I'm showing. Okay, right, so there's a specific name for a matrix that squares to 0, even though the matrix itself is not 0. You may have heard this before. You may encounter it in a problem or two in quantum. This is sometimes called a nilpotent matrix, a matrix that you can square and get nil or nothing. So matrices can have divisors of 0 is the point that I was fixing. And we see that they are not a proper field. Okay. So tapping back over to the slides. So we talked about divisors of 0 and the properties of fields. And then with field technology, we're able to define a vector space, which consists of a field of scalars, like the real or complex numbers, and then the vectors, which we are working very hard to consider an abstract space and disassociate from arrows. And then the extra algebraic piece is that you need a method of multiplying scalars times vectors that has to respect all the standard properties. Okay, we talked about ket notation and sort of the philosophy behind this, that the expectation value or the average is the thing that's well defined in quantum mechanics, so that has a simple interpretation. But the natural degrees of freedom in quantum mechanics are amplitudes and not probabilities. So that leads you to want to take a bracket and split it in half, if you could, and talk about the vectors as kets, half of the bracket, and their partners, called bras, as the other half of the bracket. So we will continue to practice this notation. And then we work out several properties about the additive identity being unique. That was true at the level of a group already, since it only needed one algebraic operation. The additive identities being related to one another, so this really required the technology of the field. Excuse me, the technology of the vector space. This is really scalar times vector multiplication. And the relations of the additive inverses, that when I write the ket negative v, that means the additive inverse of v. It's a different statement to say that that additive inverse is obtained by multiplying the vector by -1. And that statement is true. We showed that last time. And then similarly, the additive inverse being unique. Again, this was a property only of the group. So we also introduced the idea of linear dependence and linear independence. We went through a couple of examples of vector spaces, and we said linear independence is really a statement about cancellation. This is the closest that you can get to defining how many directions there are by defining what can and cannot cancel each other. So sort of two directions are independent if this direction is incapable of ever canceling that direction. And that's the generalized concept of linear independence. That applies not only to vectors in three-dimensional space, but functions like sine and cosine with different arguments. They can all be regarded as vector spaces with linearly independent vectors. So once we have the concept of linear independence, which mathematically meant that if vectors are adding up to 0, the only way that's possible is if all of the vectors have 0 weight. So if the vectors are uncanceling, then these scalars must be 0. We went through a couple of examples of linear independence, matrices, as well as the original vectors, as well as polynomials. Anything that cannot cancel is linearly independent. And then we use the idea of linear independence to build a dimension, or to build a basis for the vector space, to tell you how big the vector space is. So we said the dimension is defined to be the maximum number of linearly independent vectors. And that should agree with our intuitive definition from arrows that the dimension of a vector space like R3 is equal to the number of independent directions in that vector space. And that corresponds to the concept of linear independence. Okay, and then I believe we stopped going through the exercise to show that there cannot be a fifth linearly independent matrix. So we were talking specifically about 2x2 matrices, real 2x2 matrices. We said here are 4 vectors that are linearly independent. You can clearly see that they cannot cancel each other. And I think I can take any vector and write it as a combination of these 4 vectors. And we showed that even though these 4 are linearly independent, any fifth you add would not be. And because 4 is the maximum number of vectors that you can fit in this vector space that are linearly independent, the dimension of the vector space is 4. Okay, and I think that brings us to today. Any questions left over from last time? No, okay. So, I'm not sure what the best way to do this is. Can I put this side by side and try and draw on the right? It's not going to be too small. Can you guys see this okay, or is this too small? Should I try something different?
It works for me. If you draw large enough on the right.
Okay. So I'm going to draw large enough on the right. Okay. Okay, great. So now that we've talked about dimension, we can use that to construct the notion of a basis. And a basis is a very powerful concept in linear algebra, and change of basis between one representation and another is something that we're going to be doing a lot throughout the course of the year. So a corollary, which is more or less along the lines of what we just showed in the matrix exercise, is that if you have n linearly independent vectors in an n-dimensional vector space, you can always expand a vector in terms of that set of linearly independent vectors. So if I have dimension n, if I have a vector space with dimension n, let me write it capital N for clarity here. If you have a vector space with dimension n, any set of n linearly independent vectors can be used as a basis. Constitutes a basis. And what that means is that you have the ability to expand any vector in the space as a linear combination of those independent vectors. And expand any vector cat V that lives in my vector space capital V as a linear combination of the basis vectors. Okay, I think that's what I said on the slide. So if you know the dimension is n, and you already have any choice of n linearly independent vectors, then you can, in general, decompose your state v or your vector v as some unknown coefficients times whatever your linearly independent vectors are. So, for example, this could be I hat, j hat, and k hat, your usual three-dimensional basis vectors in R3. They could also be the four states that we talked about a minute ago for the 2x2 matrices. Let's see, 1, 0, 0, 1. Sorry, 1, 0, 0, 0. This is a different basis. 0, 1, 0, 0. 0, 0, 1, 0. And 0, 0, 0, 1. These bases are particularly nice ones. These are orthonormal bases. We'll talk more about that after we define what a norm is supposed to mean. It doesn't have to be this pretty. Any complete basis will work. So I could have equally well chosen, instead of these four very pretty matrices, I could have picked, I don't know, 1, 0, 0, 0, 6, pi, 0, 0, 84, 17, negative 2, 0. You get the idea. The matrices can be as messy as they want, as long as they are independent of each other, right? Like this one only has the 1, this one has something in that other corner. These guys will never cancel each other, so they are linearly independent. For the same reason, even if these guys are way messy, if I add in something new, it's still going to be linearly independent. And so if I fill in a fourth basis vector, I don't know, 8, 7, 9, 5, whatever, then these four vectors will also be linearly independent. So this would be, say, 1 prime, 2 prime, 3 prime, 4 prime, where before we had referred to these guys as 1, 2, 3, 4. And so the statement is you don't have to have a pretty basis. Any basis will do as long as they're linearly independent. And then I can write this large. I can write any vector v as some combination of those vectors. So I could decompose any 2x2 matrix in terms of my 4 vectors 1, 2, 3, 4 that we defined on the previous page here. I could equally well take the same matrix and write it as a linear combination of the new messy vectors that I worked on, 1 prime, 2 prime, 3 prime, 4 prime. So, of course, when I do this, the coefficients aren't going to be the same. So what we said was any vector v can be written as a linear combination, meaning there are coefficients v1, v2, v3, v4, or I could have written it instead v equals v1 prime, 1 prime, plus v2 prime, 2 prime, plus v3 prime, 3 prime, plus v4 prime, 4 prime. So it's obvious to say, especially when you think about three-dimensional vectors, but when you deal with these abstract quantities, you can easily become confused. Of course, these coefficients are not the same. If I pick a different basis to expand in, then the coefficients are going to be different. So some bases are more convenient than others, and we will spend a great deal of time finding the most optimized basis that you can use to answer a particular question. And part of the difficulty in quantum mechanics is that those bases that you would like to use to answer questions can be mutually exclusive. So maybe let me add that comment here. You want the best basis for a calculation. But in quantum mechanics, many observables are mutually exclusive. And what this will mean for us is that when we define an observable as a matrix, so if I have an observable O1 is some matrix, and if observable number 2 is some other matrix, blah, 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 then we will run into this problem if the two observables don't commute. If the commutator of O1 and O2 is not equal to 0, then they are mutually exclusive. And so that's part of what's going to make this problem prevalent in quantum mechanics, is that when I want to describe an energy that has one natural basis, a Hamiltonian matrix that has one natural basis, and I've got other operators like spin or angular momentum or something that have a different natural basis, I've got to jump back and forth from one to the other. So using different basis expansions and converting from one to another is going to be a very important exercise for us. Okay.
Can I ask, please?
Yes, please.
Is it important for us to know the difference between the pure state and the mixed states? If we use...
Can you tell me a little more by what you mean by that question?
For each vector, we mean... for each vector is a state.
Yes.
So if the vector just depend on one base, for example, if it is V1, kit1, just like this one. Is it
so
pure state?
When we're talking about quantum states, so we can say that this is some quantum state V, and V is written now as a superposition of other quantum states. So you might say V is not a pure state. V can be written as a superposition of these basis vectors. Right now, this is always true, right? So any basis you could pick, you could write this down. So I don't think pure or mixed is meaningful unless you're talking about pure or mixed with respect to a specific basis.
Yes.
Probably you're talking about the basis of the Hamiltonian, which is the one that's stationary in time. So then I would care a lot whether I am sitting in an eigenstate, if these basis vectors are the natural basis of the Hamiltonian, then it matters a lot whether these are equal to one stationary state of the Hamiltonian or if they are mixed and then this component has one time dependence, this component has a different time dependence, and then the whole thing is not stationary anymore. Is that what you're referring to, Mohan?
Okay, thank you. Yes,
Okay.
almost.
Yeah, so we will come to that specifically when we talk about the importance of the Hamiltonian for time dependence. For now, this is just a general statement. Cat. I don't need your help. Okay. So, just a simple comment to tie this back to elementary mechanics. Our 200 level students are doing basis transformations all the time, although they don't necessarily realize it. In our quantum mechanics notation, for instance, a standard problem in elementary physics is to take the gravitational acceleration g vector, which I've written here as g the cat. And the first thing you do is to rotate your coordinate system and ask how much of the gravitational acceleration points down the ramp in an allowed direction of motion versus pointing into the ramp and is forbidden. This is nothing more than a change of basis to describe the gravitational vector g. So in the natural basis, the natural Cartesian basis, which I'm writing as ket I and ket j, the acceleration is just minus 9.8 meter per second squared in the j hat direction, as everyone knows. In the rotated basis, now it has both I prime and I prime and j prime components. So now it is minus 9.8 meter per second squared times sine theta and cosine theta along the two directions. So this isn't necessarily how we teach it to our 200 level students when they're first taking this, but this is a statement in vector theory or in abstract algebra that I am taking a vector, the same vector, and representing it in two different ways. And for this problem, this choice of basis is far more convenient. For a different problem that didn't have that ramp, you would never choose this basis. You would always choose the standard one. Okay. Examples of bases. So when you do this, when you pick a specific basis, all of the information about the direction of the vector is just contained in those coefficients. So if I go back to this. Yeah, so the power of a basis is that you're sort of picking up a unified frame of reference to describe all of the vectors in a space. So if you use a common basis, for multiple vectors, such as for all vectors, then the only difference between vector v and vector w as written here is the difference between those two numbers. So go back to here. So if I have vector v equals, I don't know, 3 in the one direction, I don't know, I think the 1 is going to get confusing. Let me call it ijk for a second here. Plus 4j plus 5k. And I have some other vector w, I don't know, 10i minus 6j plus 2k. Right, so the only difference between these two vectors in this common basis is those three numbers. So when you choose the basis, you're essentially reducing the vector down to just a set of numbers, the set of those coefficients. And we saw already that the set of ordered n tuples is a vector space. So it's sort of like taking an abstract vector space and removing the basis vectors. And then the only description left is in terms of what the coefficients are doing. And then you can talk about the entire vector space just by talking about the coefficients. And so I think formally this is saying that I am going from one vector space, which is the vector space including all of those cats, to an equivalent vector space that just knows about the components. So this is useful. I think it helps to think of those components as a column vector. So let me, for instance, rewrite vector v as matrix multiplication of a set of coefficients, 3, 4, 5, times, here, actually, for the purposes that I'm going to write here, let me do it the other way. Sorry about that. I, j, k. And then I'll write the coefficients as a column matrix. you can see, the row versus the column is totally arbitrary. It's a choice of convention. But this is the standard convention, to think of these as being the vector itself as that column matrix of components. Okay, so the idea of the basis is pretty familiar, and we're all used to taking advantage of exactly this kind of description. So the point is now to use this machinery to define a norm, or to define an inner product, a dot product on a vector space. And this is going to come in several steps that are conceptually quite subtle, and I want to try and at least give you a flavor of what's going on here instead of just saying, I make up a vector product and this is what it is. So what do I mean when I say an inner product? I mean something which is a generalization of the common notion of a dot product in 2 or 3-dimensional arrows. So normally we think of the dot product A dot B as telling you how much of A and B are parallel to each other. Right? It's the amount of work in the direction of displacement. It's the parallel components. So you can use this, for instance, to write down an expression in terms of the angle and the magnitudes. It's okay. Let me stop talking and start writing. For the inner product, we usually think of A dot B as magnitude of A, magnitude of B, cosine of the angle between them. The more useful expression for us is the one in terms of components. AX, BX, AY, BY, AZ, BZ. There's lots of different ways that you can imagine defining a dot product, right? So like, I write down 2 formulas. Which of these is the correct definition? It goes either way. You could say I define the first line is the definition, and then I work out the algebra and the second line follows. I'm going to take the opposite point of view. I want to use something like this to define in components what do I mean by the dot product. Define A dot B through a relation like this. And then once you do that, if I know what A dot B is, that serves now to define what a magnitude is. Defines magnitude of A and magnitude of B. So these concepts are equivalent. As soon as you have a concept of distance or a metric that tells you how large the magnitude of something is, that's equivalent to specifying the dot product. For the moment, we are not going to specify exactly how to form the dot product. I'm not going to specify that the formula looks exactly like this. But let's suppose that there is a formula that we pick. There is a formula in terms of these components that will let me take any vector and calculate these. Based on its components, calculate the dot product of 2 vectors. And then from that, we define what the magnitude is supposed to mean. So conceptually, I want to emphasize the aspect of the dot product as parallel projection. I think that's the part that carries over to quantum mechanics. You can't think of the angle in between when I have an n-dimensional complex vector space, but I can talk about how much of vector A is pointing in the same direction as vector B. That still works. So that is, in essence, what the dot product is also telling you, that if I have 2 vectors drawn A and B, the usual formula AB cosine theta is telling you if I take vector A and I ask how much of vector A is projected along the direction of vector B, cosine of theta will give me this component here. So the length of that side of the triangle is A cosine theta. And that vector here is A cosine theta, and then I put it in the direction of B. So just semantics perhaps, but a way of rewriting the dot product A dot B is to say that this is equal to the parallel component of A times vector B. You could also swap it the other way and say that it's the parallel component of B projected onto A. But this is the language that I'm going to use going forward, that your inner product is a projection operator. Maybe projection operator is not quite the right way to phrase it mathematically, but it is a projection of one vector onto another. So when I write something like A and B next to it, I'm going to think of this as a notation that I will use for saying that I have vector A and I want to project it onto vector B. So defining the dot product is going to be telling you how to write the brackets together, and that's essentially defining what we mean by parallel projection. Okay. And then, as we already talked about, once I define what parallel projection means, I can define the length of a vector, a magnitude of a vector, by using, seriously, in the way. You can define the length of a vector, its magnitude, based on the parallel projection with itself. So this is how a generalized dot product will be used to define a metric or a distance concept, a length concept in your abstract vector space. Okay, so the properties that we are going to use for our inner product are going to look a little bit weird because we need to set up an inner product that will be useful for quantum mechanics and not classical mechanics. In classical mechanics, we are dealing with real vectors, like a field of real scalars times vectors. And as we discussed a little bit before when we introduced the Brockett notation, that's not going to carry over terribly well to quantum mechanics. That in quantum mechanics, the expectation value may be real, but the natural degrees of freedom are complex. And this comes from wave-particle duality. The fact that my wave intensity is written as the square of the amplitude. So, okay, let me write this out. In wave mechanics, you have something like the intensity of a wave. Intensity I is proportional to an amplitude squared. Wave amplitude versus wave intensity. So this is true for light. If you want to talk about how much power is carried by a beam of light, then that power means you're talking about the intensity. If you want to talk about the phase of the wave, interference patterns, that's going to come from the amplitude. Right, so waves have an interference pattern based on the phases of the amplitude. So for waves, it matters a lot whether I'm adding sine with another sine in phase or whether I'm adding it with cosine, which is out of phase. So if the amplitudes are in phase or out of phase, then that's going to change the answer. So the amplitudes really matter, but the thing that actually carries power or intensity, that's just going to look like this. Right? It's going to be positive, and it's going to be concentrated wherever the overall wave intensity is the highest. So I say this to motivate why we need to consider a complex metric, a complex inner product. That in general in quantum mechanics, even though the intensities are going to be real, probabilities are still real and positive, the amplitudes are not. And so since we're dealing with complex numbers, we have to consider what does it mean to have a dot product that is complex and what properties we require of a complex dot product. So in order for the idea of a magnitude or a norm of a vector to even be well defined, to even make any sense at all, I have to have the norm of a vector with itself should be positive, right? Lengths must be positive. I still don't know what something that is I units long means. So even if I'm going to build a complex inner product, I need to ensure that the length of any vector is still positive. So requirements. In general, an inner product of A and B is complex, an element of the set of complex numbers. And we need to have the metric or the norm of a vector be positive. So it must be greater than or equal to 0. That's actually two conditions. So if these things are complex in general, then this thing first better be real, and it better be positive. And so that's going to require us to use a specific form in terms of complex conjugates to ensure that if I've got two complex numbers, when I multiply them together, I better get something that is real and positive. We still need some notion of symmetry in the dot product that I mentioned before when we had this parallel projection of arrows, of arrow A onto arrow B. The regular dot product is perfectly symmetric. If I take the component of A and I project it onto B, I get the same answer as if I took B and projected it onto A. If you just take that literally and you require exact symmetry, you're going to have problems with the complex numbers here. So we will show that you will get something that satisfies these properties, that has positive norm, and even though the inner product is in general complex, we will show that this is satisfied if I relax my symmetry constraint just a little bit. So that if I flip the order between A and B in the dot product, these guys are closely related, but they're not just equal. I have to introduce a complex conjugate. That's terrible. Star. And Shankar calls this skew symmetry. So this is the subtle part that we're going to have to track through where these complex conjugation operations have to get added in. This is one place. The other is in the distributed property. So I want to tell you a little bit about the concept of the dual space and about where this idea of the bras come from. If this is abstract and too technical, don't worry about it. This is conceptual that might help you understand why we're doing what we're doing a little bit better, but you don't need this mechanically to be able to calculate things. So another way to think of what a dot product is, or what an inner product is a mapping that takes you from some vector you start with, right? So it's a function defined whose argument is a vector, and the output of that mapping is a scalar. So the dot product is a mapping of any vector onto a number. Just to give you an example, I'll write this down in just a second here. So imagine that I've got one fixed vector B. I freeze B and I don't allow it to change. And I imagine all vectors A in the universe. Then this dot product or parallel projection operation is something that takes any vector A as input and it spits back out the number of its parallel projection onto B as the output. That's what I mean. It's a function of vectors as input that gives scalars as output. So, to write it out, another interpretation is that an inner product maps vectors to scalars. And we said A dot B equals number is like saying I have f of A equals some number for fixed B. This seems like an esoteric and pointless distinction, but it's helpful to understand that the function space that I'm talking about is a different space than the vector space you started off with. Right, so I have two sets to think about here. I have the original vector space V, whose elements are those cats, little v, that live inside the vector space V. What I'm talking about now is something conceptually different than that. And functions on that vector space. F, let me write it in this notation. F, it knows about B, but for fixed B, it's a mapping of vectors A to some scalar. Which map V, the vector space V to the scalar field F. So one can show, if you check all of the properties, that the space of these functions constitutes a vector space. These mappings constitute a vector space all of their own. And this vector space is very closely related to the one we started off with. They are called duals of each other. So this is the dual space. Let me call this vector space V star. And so this is the dual space V star to the original space V. So this is where bras come from. So cats are what live here. And the elements of the dual space are called bras. And so that's why they're conceptually tied together with defining the dot product. Defining the dual space is again the equivalent to defining the dot product or defining the norm. These are all different ways of understanding the same thing. So whichever way makes the most sense to you is fine. In terms of thinking about this as a mapping, the mapping has like one main argument. The main argument is V, whatever vector you pick from the vector space that it's going to map to a number. It has that auxiliary vector dependence. So here I wrote it as F sub W that depends on some vector V. So I can talk about the dependence of the function on V, and there it has to have all the linear properties that we've already talked about. But I can consider differently what its dependence on W is. So what happens if I use this mapping on a linear combination of vectors? So if I have a mapping of A times V plus B times U, it's got to be linear in that order, right? So if I have coefficient A and two different terms, then I distribute everything out and I get two different terms with coefficients A and B. So I'll write this on the notes in 1 second. So this property is ordinary linear function. It's a linear function. This property where we demand that it's linear, but any coefficients you stick in get complex conjugated is called anti-linear. So this is the other half of that complex conjugation we need to introduce to ensure that all of the wave intensities become real and positive. So to write this out more slowly, if my mapping, let me write it this way, F sub B of vector A, so if this mapping is going to be a well-defined inner product, the way that we need it to be, it has to be linear in A, linear in vector A, which means, let me write it as, say, f sub b of, I apologize for the notation, that's the first thing I can think of off the top of my head. If I have two different vectors going in, big A1 and big A2, with some coefficients, little a1 and little a2, then this needs to be an ordinary linear function. So it's a1 times f sub b of a1 vector plus a2 times f sub b of a2. So this is ordinary linearity. But if I ask about the dependence on vector b, it doesn't have to be the same. This is related to skew symmetry, that I'm imposing a slightly different condition on the bras, or on the dual space, than I am on the original space. So now if instead I have f sub, let me call it little b1, big B1, plus little b2, big B2 on any vector A, this dependence down here on the auxiliary vector that lives in the dual space is the one that is antilinear. So this is B1 conjugate f B1 of A plus B2 conjugate f B2 of A. I hope I'm not making this more confusing by giving you too much information. If all of this is just not making any sense, don't stress about it. But the point that I want to get across is that there is a conceptually different vector space. And the bras live in one vector space, the cats live in the partner vector space. And together, the two of them define what parallel projection means. And so that's why we will write it in this sort of bra cat notation, where it looks like this is an inner product built out of the bras and the cats. Okay, right, I think I actually said already everything that's on this slide now. Yeah, so this goes back to the other half of Dirac's dad joke, that by taking the bracket and splitting it in half, I end up with the cats that live in vector space V, and the bras that are the partners that live in vector space V star. And you can think of this operation as projecting vector V onto vector W. So to come back to this column matrix representation that we had talked about before, if I pick a specific basis, then I can represent any vector as just the coordinates in that basis. So if I have just a two-dimensional vector space, for example, then I can write down my vector v as just its coefficient on basis vector number 1 and its coefficient on basis vector number 2. If the vector space V is made up of these column matrices, then the dual space to it is made up of row matrices. How do I see that it's made up of row matrices? Because multiplying a row matrix times a column matrix gives you a number. I have to move this cat one more time. Sorry. Now he's clicking my mouse. So to try and write out more explicitly what I mean here, if I take V and I write it in a basis, so let me say this is V1 times some basis vector 1, V2 times some basis vector 2. Then now I can write this as, let me maybe write it this way, that my vector V can be identified with the column matrix just given by its two coefficients. And then if I have some f sub w of v, which is going to map the vector v onto some number, then I can accomplish that by taking whatever column vector I have here and multiplying it by a row vector. So I can represent this mapping as multiplication by a row matrix. Okay, maybe let me write this in 2 steps. How do you map a column matrix to a number, multiply it by a row matrix, and the point is to interpret or express f of w using that representation. Express fw of v as a row matrix. It's not just as a row matrix, but as multiplication by a row matrix. So if I have some vector v1, v2, and I multiply it by another vector, let's call it w1, w2, then I'm going to get w1, v1 plus w2, v2. This is a pretty good start. So this definitely maps vectors to scalars. That's good. The simplest thing that I can write down where I just write this as a row matrix isn't going to work, though. It's going to fail one of those detailed properties. Does anybody know what this is going to mess up?
Symmetry.
Yeah, so this property would be exactly symmetric. What we need is skew symmetry. So I need to demand that this is going to give me complex conjugates associated with whatever's in the bra, whatever's on the left-hand side. So you can think of the mapping in going from V to V star, real space, dual space, as being like taking a column matrix, V1 and V2, and then turning it into the row matrix, V1 conjugate, V2 conjugate. So this operation is called the adjoint. It's also sometimes called the Hermitian conjugate. Hermitian conjugate, sometimes you'll even see it spelled differently, and I honestly don't know which one is correct. In case you're not familiar, the adjoint or the Hermitian conjugate is formed by taking the transpose and by taking the complex conjugate. So the transpose turns the column matrix into a row matrix, and the complex conjugate satisfies our need for antilinearity. So you represent this as a dagger on the matrix. So if I have some matrix A equals A1, A2, then A dagger is equal to A1 conjugate, A2 conjugate, row matrix. And then in general, we would say A dagger is a matrix whose components ij are equal to the original matrix with I and j reversed, ji, and complex conjugate. So flipping the order here accomplishes the transpose. And taking the complex conjugate satisfies our antilinearity requirement. So this is why you'll sometimes see the notion that your cats are column matrices and that your bras are row matrices. It comes from this fact that you've got to multiply them to get a scalar out, and multiplying row times column accomplishes that. Okay, so that is all that I had in the slides at this point. The next step after this is to start talking about what happens when you change bases. So I think rather than starting this, maybe I'll just give you a flavor of where we're going to go with this next, but I won't dive into this in detail in the last 15 minutes of class. So let me... So linear transformations and change bases. There will be a couple of things that we have to talk about as preliminaries, and so this helps, I guess, define what you mean by a perpendicular projection. So one thing we'll talk about is orthogonalizing vectors. And this is essentially what we will use to define the perpendicular component. We say a perp of a vector A. And there's no magic to this. It just comes from the fact that the inner product defines the parallel part. So I can take any vector and split it into something parallel and something perpendicular. So the idea is, if I go back to the example I had before, if I had vector A and vector B, then I'm essentially decomposing vector A into a piece which is a parallel vector and a perpendicular vector. We've already talked about how to define a parallel, so you can see that a perpendicular is basically whatever is left. So we will say basically a vector is defined to be a parallel vector plus a perpendicular vector. That's just a definition. That's what do I mean by perpendicular? I mean anything that is not parallel. So if you take this as the definition of what you mean by perpendicular, your a perp is defined to be the full vector minus its parallel part. Now I know how to define this in quantum mechanics using the more general norm that we talked about, the inner product. So when I write down the perpendicular component of the vector W, for instance, right? So if I have some vector W and want a piece parallel to some vector V and something orthogonal or perpendicular, to V. And I'll do it basically using this formula. I know that my parallel projection is going to use the dot product. I'm going to take my original vector V and I'm going to project it, I'm going to take the vector W and I'm going to project it onto V. So this quantity is projection of W onto V. That's just a number. I want a vector. Right? This thing is a vector that lives in vector space V. This thing is a number that lives in scalar field F. So if I want to make it a vector, this has to be a number, and I have to multiply it by another vector. Right? This is the number of the projection, and it's in the direction of the thing I projected it on.
V.
V. Right? In the direction of V. So again, that's like talking about back over here for the arrows A and B. This is the scalar number that tells me that length. That's what the dot product gives me. If I want to make a vector out of it, I have to take the dot product and multiply it by the direction. That would be really easy if this was a unit vector. But before I talk about the correction from this thing not being properly normalized, let's just finish the expression. If it was just a unit vector, then all you would have is vector W perp. If this is what I mean by that perpendicular component, equals the original vector I started with. So we said that this is A minus A parallel, and this quantity here is basically A parallel. Let me call it A parallel. And it's a squiggle and not an equal to sign because of the normalization that we'll fix in a second. So it's the original vector minus the parallel projection. V, W, that's a scalar, times V. So if this were a unit vector, then V times V would be 1. If V times V is not equal to 1, then I need to divide by the magnitude to fix it. So we'll go through all of this a little more slowly next time, but basically all I have to do is divide that projection piece by the magnitude. That basically takes this V and makes that a unit vector, and it takes this V and makes it a unit vector too. So this process is the basis of what is called the Gram-Schmidt process. For orthogonalizing vectors. Where orthogonal means the same thing as perpendicular. So Gram-Schmidt is very helpful, but you can write it down as an algorithm for how to take, for instance, 1, 2, ... n basis vectors. And if you use this procedure, you can start with one of the basis vectors, make it a unit vector, and then you're happy. For the second vector, I want to make a nice basis. I want to make the second vector perpendicular to vector 1. I don't need the parallel piece. The parallel piece is linearly dependent with the vector I already have. So only keep that vector's perpendicular component. That maybe isn't a very useful way to write it. Only keep perpendicular piece. And then we make it a unit vector. And then again, I will be happy with this vector. These two vectors will have length equal to 1, and they will be exactly perpendicular to each other. So based on this idea of finding the perpendicular component and then repeating that process, you can turn any set of vectors into a set of orthonormal vectors. So you can transform any basis into an orthonormal basis. Where orthonormal means that your basis vectors, let's say I have the set 1, 2, ... n, that any of them with themselves have magnitude 1. And the product of any one of them with any other is 0. So again, this is sort of a technicality, but once you have the concept of a dot product or a parallel projection, that gives you everything you need to define perpendicular, and that gives you everything you need to take any basis that you're handed and convert it into an orthonormal basis. So for many purposes, we will be assuming that you've already done this, that whatever basis you're going to work with has already been simplified this way to become orthonormal. And then if I'm talking about one basis versus another, all I have to do is talk about the coefficients that transform from one basis to another. So suppose I have two representations of the same vector. So let me expand vector v as v1, 1 plus v2, 2 plus dot, 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 plus vn, n. And I write it also in a different basis that might be useful for something else. I write it as v1 prime, 1 prime, plus v2 prime, 2 prime, plus dot, 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 plus vn prime, n prime. How are they related to each other? That answer depends on how the basis is related to each other, right? So this is just a number, this is just a number. The fact that the bases are different from each other is because these vectors are different from those vectors. So to answer this question, I need to know, what does the new basis look like in terms of the old one? Basically, what this means is that I can take any of the basis vectors that I want to know, and I can expand them in the original basis. So I can write that basis vector 1 prime as some new coefficients. A 1 prime 1, 1 plus a 1 prime 2, 2 plus dot, 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 plus a n prime n, excuse me, 1 prime n. So all I'm saying here is, if I've got a complete basis, I can write down any vector I want using it. So you can do that to express the new basis in terms of the old basis. And when I do that, I'm going to get a big mess of coefficients, right? I'm going to get v equals, and instead of v1 times 1, now I'm going to get a whole mess. I'm going to get all of this stuff. For example, I'm going to get v1 times whatever that original, whatever the basis vector is. So I'm going to express the second line in terms of the first one. That's what I should say. And using this expression for 1 prime, I expand it out and get a 1 prime 1, 1 plus a 1 prime 2, 2 plus dot, 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 plus v2 prime, and now again, 2 prime can be expanded. All of these things can be expanded out. 2 prime 1, 1, 2 prime 2, 2, plus dot, 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 plus the n prime times a n prime 1, 1 plus a n prime 2, 2 plus dot, dot. Okay, so this is coming at you fast, but what I need to show here is that if I take two different expansions of the vector and I express one of those in terms of the other, what I get is like a big matrix of coefficients. At the end of the day, this is going to equal some number times 1 plus some number times 2 plus dot, dot, cat. And those overall coefficients are the ones that we'll call v1, v2, and so on. So what this looks like at the end of the day is a matrix transformation where it tells me v1 prime, v2 prime, let me write it this way, v1, v2 dot, 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 vn equals a matrix times v1 prime, v2 prime, dot, 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 vn prime. And all of the numbers that go into that matrix describe the transformation. So there will be a great many important change of basis transformations that we will need to make, especially because in one basis, one set of observables in quantum mechanics will be diagonal. In a different basis, another set will be. So we will need to use and freely transform back and forth from one basis to another using this method. And the symmetry properties of that matrix will determine how those transformations work afterward. Yes, question.
Is it just like with a conversion between the vector from Cartesian to spherical, but the length will stay the same?
Yes, that's exactly right. So Cartesian and spherical are two choices of basis. And so that transformation is exactly what I'm
The length should be the same.
Yes. So in any basis will preserve the norm. That's right. So there are conditions that the matrix I've written here, A, must satisfy. It will satisfy because the transformation preserves the norm. It has to keep the inner product invariant. That's right. So you can think of these as generalized rotation matrices, if you like, since the rotation is what preserves the norm. Okay, we are out of time for the class. We will go through the linear transformation stuff and the Gram-Schmidt process more carefully next time, but I wanted to give you a little bit of flavor of where we're going next. Any questions or new business that you want to bring to my attention before we adjourn? All right, thank you all very much. Thank you again for your patience in bearing with me. It's going to take a few weeks before we are converged on what actually works best for the class. Here, maybe can you guys tell me with like a yes/no answer, does this writing on the board help? Do you like this? No.
Yeah, I like it much better personally.
Okay.
Yeah.
I see some yeses and some nos.
I think the concept was really good. The execution was very poor, especially because you had to, start writing and then you'd move away from that and start jumping around. I think one concrete thing you could do differently is like instead of splitting up your screens from the left and right, split them from top to bottom. That way you have two kind of like landscape orientation windows, and you can work Blackboard style in one and have the slides in the other.
I like that idea. I think that's pretty good.
So I hope next time that I will not need a full set of slides, that I can do it almost entirely on paper like this. What I would want to do is have any like figures that I would want already pasted in. And so then it would be like the slides, but mostly blank. And the only thing that I would have on there would be special figures that I need to draw ahead of time. So we can try that on Tuesday and see if that works. Hopefully it'll slowly converge. Yes, I will certainly upload all of the supplementary material and everything. The slides are the same as from last time, but I will certainly upload this as a PDF. All right, thank you, everybody. I will see you on Tuesday.
Thank you, Professor.